continuing at Brandeis, what formerly was the demo lab, and which is now called the Big Lab. So without any further ado, Kyle.
Okay, so I'll skip this. Alright, so I'm going to be talking about embryogenesis-inspired computation is what I call it, and I just have to give credit to the people I've worked with on this. Obviously, women's the one that got me actually doing embryogenesis, and I did that while being advised by the inspector and now doing journal college at Brandeis. So that's that. Alright, so getting right into it, talking about multicellularity, kind of one of the first questions I want to ask is what are the origins of multicellularity? I'm not going to talk about the biological basis of it because I don't know all that to be a scientist. So I'm just going to talk about the things I've seen in artificial life and how they're going to be combined into my project and some projects. But okay, so we have Tierra, and Tierra is kind of one of the first places I've seen evolve multicellularity, where you have your grid cells and they have the ability to divide and interact with the cells they divided from. So, and I haven't read anything about them doing anything, forming any of these large organisms. It doesn't really have the physical simulation that I'm interested in, and it goes on to division blocks, which is a project done in Breve, and that's interesting. It's a project done in Breve, by John. And so the interesting thing about Breve is it's a 3D world that has full physical simulation. And so in this world you have these blocks. You start off with a whole bunch of blocks on a platform. And they're photosynthetic. You have a sun that rotates around this world. And as they grow, they get energy, they can divide, and they can maintain links to their previous blocks. And they can exert forces on those things. So another part of it is that it has open-ended evolution, saying that it doesn't have a fitness function. You just have these blocks that grow, and as they grow more, keep growing more, and take on other blocks. So it's potentially interesting, but we haven't done anything interesting about it. This is a project being done by the inspector of college, and it has potential, but it's going to be more processing power, basically. So now we'll get into the various ways. So you simulate multicellularity. It's been simulated in a variety of ways. You have cellular automata, L systems, which is a technique that's been used a lot of Brandeis. You have various types of cellular encoding, cell chemistry. You have gene regulatory networks, where you just have sets of genes and your regulation of the genes is a morphology later on that can cause different types of differentiation. And the method I'm most interested in is the cellular possible, which is you have a lattice of cells. In general, it's a 2D model, it's done in 3D. And so you have a bunch of cells there, and as opposed to doing the standard process of like with a cellular automata where you go and you update every single cell in one iteration, and then you step into the next iteration. Cellular POTS model, you go probabilistically one cell at a time. So you get a little bit more non-determinism than you would in these other methods. So, and you also have this Hamiltonian, which is a relation between the energy values of various neighboring cells, and it ends up giving you a probability of accepting an update from the program. get much more closer to reality by doing this one at a time. Because order ends up mattering, then if you have this everything being updated all at once, then you can get relations. Then they kind of depending on having that entire update happening as opposed to
is the order fixed at the start and then remains it, or each tick is a new random order that's updated?
it's a new random order. Alright. So artificial embryogenesis. So it's the idea of you develop an organism from progenitor cell, and it grows into a larger organism with a variety of cells, with a number of cells. And so it's a technique that it's not specifically about growing a physically based organism. You use embryogenesis techniques to grow a neural network or modeling crystalline growth. So it's more of this developmental sort of thing than anything else. That's what it is. So the focus of the research I'm doing is less about all of these other types of embryogenesis. It's about, I'm more interested in actually mimicking biological organisms. So I would like to have modeling, for example, a brain-based sort of world where you have a 3D model and you can grow something potentially potentially an insect, but growing from an initial insect. So that's what I'm interested in. So this is the research that has kind of inspired a lot of things I'm doing. And I'll just show you I had to figure out how to mimic this more than 20 parameter model. So it's a model developed over at the University of Zurich, where it starts off with an initial stem cell, it grows into a full organism, and it mimics a Breitenberg gene. It exhibits pathfinding abilities, it has motor and sensor system, and we'll get into that later. So this is how the growth begins. So you have a cell lineage tree. You start off with a blast cell, which is kind of like a stem cell, but it has nothing unique to it except it has the ability to divide, and so it has that loop. It can make more of itself next to these other blast cells that will stand later, and to get into a constructive cell. So over here you have it's actually a 2.5-dimensional environment, but I can't show the half dimension. So these cells are in the 2D and they can move around, and as they move, they can potentially stack over their cells, but due to free energy constraints, they tend not to stack because it's more energy to stay stacked over the cell. So that's the basis of it. So you start off, you grow, it's divided into other cells. It divides into other blast cells, the yellow pieces, and it has these sort of structures over there. And this one's slowly skeletal. And due to the fact that this is a very simplified model, you can't have anything that shows skeletal. But it is an unoccupied structure for these other systems. I should also say that all of these cells produce what's called an organism, which is essentially a chemical. It has a property where it can diffuse along this network, so it's produced inside of a cell. It can diffuse out of the membrane of the cell and along its lattice. And that is essentially what triggers when the cell switches. So once you have enough of this morphogen for the initial blast cell, you will trigger the growing of the disruptor cells, and eventually later on you trigger the growing of other blast cells. So here we go, we have the beginning of the structure, and we move on, we have the structure developed, and here we have, you see the blue and the red, those are two different pathogens that are triggering blast sensor and blast motor cells. So right there, the circuit cell is one of the first blast motor cells. And the organism isn't getting very interesting yet, it just kind of sits there in its environment. So you have the blast motor cell, and then you start growing up and you have motor cells developing on that side, and sensor cells developing on the other side. And the way you can see the equations of Kagan's paper, but you have an atom, the morphogens end up dividing along the axis, and every cell produces these morphogens, but due to its current environment, it changes which morphogens it produces at which rate, and that allows you to get this division.
Mentioning certain things that happen, you have a regulation, they induce motor cells and so on. How much of this is evolved and how much is defined top-down?
This is all defined top-down, but it is in some sense a bottom-up network. You can start with this. You start with a single cell and it's based on its environment. It has no top-down information. It only has information from its local environment. And there is a little bit of this model that is evolved. That's later. Actually, that's in the next slide. So this is when the organism has reached its maximum point. So you have fully developed motor cells over there, and you have fully developed sensor cells over there. And you have axons and neurons. So if anyone's familiar with the Brightburg so you have your various ways of wiring the sensors and motors. This is just taking it a lot farther. So you have your sensors and motors all wired, and based on the angle that they're wired at, which exerts an influence on the entire organism.
How do these axons develop?
So they grow. They grow in multicolor fashion, but along the lattice, but the way in which they grow is all genetic. So that they couldn't figure out a way of defining that beforehand, so they just had to evolve. And one thing about how this organism moves is when a force is exerted, it operates on the entire organism. So the organism is sort of in a separate lattice on top of the world, like this. So when it exerts a force, it exerts it on this local environment, and it can sense the world environment. So that's how it goes, and once you start running it, it will follow the path, and that's kind of as exciting as this gets, which is pretty neat.
The world has this figure eight or whatever on it, and then the sensor cell or something.
They can see how they can see the lightness, and that lightness is transmitted and corresponds to the force being exerted. Alright, so that's this problem. And basically, for RU about I was told to replicate this. And they wouldn't tell me any parameter settings or how they're all connected, they just gave me the equations. So I started out and I got interested in something a little different, but I'll explain what that was. So here's my version just to prove that I did it. So I have this environment, your external environment, and because I got interested in sensors, this is where the sensor interpretation ends up being, where the sensor view of the world is. And I'll explain that a lot more later. Half of this presentation is actually just about sensors. So this is where it grows up. You have the initial sensor blast cells. You have an initial sensor cell. And you have a full organism. Mine wasn't as beautiful as Fabian's, but I also didn't get the same parameters and you can tell me what the parameters are. So that's how I define myself.
Why is the external environment?
The external environment is changing here, and it's actually, the sensors in this picture are even broken. So if you see that there isn't actually any red there, but it still sees right.
But the external environment is different than it started, so is it
So because I said most no motor cells, what I did was I just had a dynamic. So I just simulated as if it had
So, question about the sensor. Question about the sensor cells. What is it exactly that they sense? Do they just sense directly below them?
They sense directly. And in the original work by Fabian, the sensor cells can only sense a single value, a single color, and I got interested in having them have more colors. Alright, so here's a video of the road. And I have a different external environment in this case. So they grow up. You have initial sensor stem cells. There's very important sensors over there. I'll show you what the sensors are.
So what is this trying to do? Is it trying to recognize the face, or?
It's actually not even trying to recognize the face, it's just trying to see the face. And it doesn't even have any reason to see the face. In the original paper, they just had it hard-coded that if you see green, that means go. So that's the principle they were working on. So, yeah. And so this is kind of an interlude because it kind of turns into a slightly different project, but entirely focused around the sensor cells. Okay, so yeah, it's about the sensor cells in the system. So here's what I got interested in. So the problem with humans is, so we can see about 10 to the 9th bits at our retina. It goes down to 10 to the 7th because we get to the optic nerve. And the visual attention section, which is further back in our visual cortex, we can only see 40 bits, is what they say. So that's kind of an issue, but I mean, even if that number isn't right, we still know that there is a huge loss of information from what we can actually see. We don't look at everything.
How do they estimate 40 bits per second? What does that information actually look? Excuse the
that was
term,
a
but look like.
study. So it was
That's
based
pretty
on.
slow.
I can't give you the full extent of the study, but you can.
Like we see through a 300 baud morning.
Yeah.
That's scary.
So in computer vision, I mean, you have similar issues because processing 10 to the 9th bits is still a fairly large issue. So this is kind of the perspective I started to take on it. So if you think of a sensor with multiple nodes, so this is different than the eye because you have the rods and the cones, and the rods are detecting the brightness, and the cones are detecting different colors, and they're detecting specific colors. So it's kind of weird to say that you have a red mode, a green mode, and a blue mode all going into the same sensor. But when you think of the camera, every pixel has red and blue in the same place. In the final image, not actually at the so this is the perspective I take. Alright, so if you have all that information, you kind of have to figure out what you want to ignore. So if you have a 2D grid of all of these sensors, and every sensor has a set of red, green, and blue colors, the way you can compress information is by A, throwing away colors at a given sensor, B, throwing away sensors completely. So I got into this notion of adaptive multimodal sensing. So you observe fewer than the possible modes, and that's a way of using less bandwidth than actually observing everything. Straightforward, but how do you select which colors to actually watch, and how do you select which sensors to turn on? And well, okay, so I should explain why this is actually interesting. So if you have that little organism which only has a few sensor cells, and that can't actually see much of its environment, and once you start to scale this organism up, you're going to have to get more information from the environment. If you're going to start looking at more complex environments, like robots, dealing with objects, or anything, you need to be able to reduce the visual information it has. So you have to select which different modes to look at in your colors. And I'll talk about how we select which sensors to look at later. So what do you want to look at? Do you want to look at the brightest things, the darkest things, the most dynamic dynamics, least dynamic, and the more random stuff? And what do you decide? So okay, so what the initial research has been is they look at essentially the brightness and to some extent dynamics. And that's where I'm going to look into as well. So what I say you need to do, as opposed to only having information that you can see at a given moment from a sensor, only operating on that, instead you form some sort of memory. So you store the values you've been seeing, and you use that to figure out what to look at. It seems to make sense to me at least. So they're stored in what's essentially a geometric series. And so you have a learning rate, you learn some subset of, or you learn a little bit of what you can see at a given point in time. And you have this gamma value which says, so I definitely should have said that alpha is always less than 1 and gamma is always less than 1. So, and greater than 0. So you can do so what this value does, the gamma, is your expectation is kind of what you used to know about the environment. And so you add what you're seeing now to what you think is in your environment, and you store it all in this chemical. I call it chemical here, it's also memory. Keep it a chemical paradigm because when it's actually set up on this lattice, it still has these diffusing properties. So I call it. So this is
SA.
SA is the actual value base. That's the sensing activity.
Is EA
Expected activity.
the previous value, or
It's based on memory. So it's kind of part of the base value. It's based on the previous value. It's based on the memory. And so this technique is actually kind of similar to reinforcement to some extent because you could actually treat this as a reward. You say it's remembering some reward and it's like an expectation of this reward. And that if you're familiar with reinforcement learning, this is actually essentially value function. So I use two methods. One that is faster, it diffuses faster along the lattice, and one that diffuses more slowly along the lattice. And I've been working around with the parameter space. I've also been playing around with the concept of memory. So you have longer memory retention rates. So this is what the chemicals look like in different sensors. It's not memory services. So this is a sensor that is observing rotating circles that are passing underneath. There's a red circle, a blue circle, and but this is just observing a single pixel that's passing underneath. So I'll show you later the difference between the actual values and expected values. So this is how the memory interacts. So you have the dark ones of each color are the long-term memory, the slow memory, and the light colors are the short-term memory, the fast memory. So the way this essentially works is, so you have these at the bottom, your short-term memory dips down further than the long-term memory, and based on the intersections between the short and the long-term memory, you can trigger whether you should be observing a given color or not. So, because with greater change, they stay parallel. So, while they're changing, your short-term memory will be greater. So this is the values that are actually passing underneath it. The light colors and the solid lines are the actual colors that are underneath the sensor. And they're a little noisy because I added 10% noise to the system. And so I also should have said that this given sensor can only hear 2 colors of the given network. And so, but you should also note that this sensor is part of a network of the sensors, all of which are observing things, all of which are taking their chemicals and they're fusing to their neighbors. So it's utilizing neighborhood information in order to trigger when it should look at the color or not. And so you can see in this first peak of the blue, it actually wasn't observing any blue, but it just had memory, which is used in order to form its prediction. And you'll see the sensors in action later, and this will make more sense. Maybe I should have done that before this. So this is essentially how the predictions are formed, and you see them in action because it's really hard to understand what's happening from a single sensor. But there's this notion of saliency maps, and a saliency map is essentially ranking a sort of all of the sensors in the network, of which are the most important ones to look at. And the way you do that depends on what researcher you're talking to. The original folks, they had to take into account color, brightness, and multiple scales. So you have pixels and so you have ones that encompass larger regions of pixels. So that'll give you additional information by having those large sort of averages of So this is how using this method, you can figure out what sensors you want to turn on. So I simplified it because I was working in a simple environment where, so you only have 3 colors and you're only working with 1 scale. And what I ended up, the interesting thing I've been able to find in this research is a way of a parameter that allows you to adjust between whether you're looking at, or whether you should have the sensors look at the brightest objects or the most dynamic objects. So ranging this parameter from 0 to 1 allows you to, instead of 0.5, look at the brightest and most dynamic objects. Alright, so this is it in action. So you have your original observation. This is much more complex, many more pixels than that original organism. But it's still observing a dynamic environment. Here it's observing a news anchor. So you have this set of observations over here. Most of the sensors are on, but they're all observing 2 colors at any point in time. So you have all these observations, and your chemicals are working behind the scenes. I'll show you what the memory is looking like in a few slides. And you form an attention map. In this case, it's looking at dynamics and actually darkness as opposed to brightness, like in this case. And so this is when it starts off observing the video.
Veggie burger and mayo?
And so an interesting thing that you'll start to see here is, so you have these sort of weird changes in color over time in the attention map. And they're kind of stark contrasts there. And that's actually the temporal encoding to some extent. Well, it is the temporal encoding. you see these edges that are, the sensors have looked in this area, and the wave activity is coming along the brighter edge. So that's where sensors will look next.
So what you're saying there is that in the lower right there due to the dynamics of the seed.
Yes.
The changes of the seed.
And its values are stored in the memory.
Yeah.
So you have these single values of the memory, and that are actually storing the dynamics, but it's a single value, which is what makes it interesting.
Does the organism cover this whole area, or
Right. Well, so basically in this part, what I've done is I've thrown out the organism that grows up in only outside cells.
okay?
So they do, yes, they do cover that whole environment.
It's the world expansion, that is, you're showing multiple
So this is an even older version. So this is when I couldn't get the predictions to the right place. But I was starting to be able to get interesting sort of dynamics. Because, so this is based on the memory, and that's actually, so that picture never really showed it's a transposition of multiple frames, but it still kind of looks like the object. That's why I thought it was yeah. And this is another project that's not quite done, but I was trying to put it into a array environment and have it drive actual training. And so this object's partially constructed, but there was a weird issue right there with the order. I think John said it was like probably the ordering in which the texturing was being done. I see that a long time ago. Anyway.
Sorry. I didn't know this was a forum for bug reports, but
Machine's coming. Machine's coming. Don't video this? I want to see someone do a whole presentation out of Emacs and VI, and I think that would be awesome. M-Player on there? M-Player always works.
Yeah, M-Player should do it.
If you like bang your hand down on the keyboard a couple times and save it to a file, M-Player will play it.
M-Player is not necessarily saved to the external monitor port.
Yeah.
That's the problem I have.
M-Player will play Commodore 64 music files.
HBO space extra. Sometimes you need that to give the experience.
There you go. See, I told you.
Alright, so I wish it was a flow better, and this is going to take a little while because it's running pretty slow. So I guess I should technically take questions. Well, I'll tell you. So, all right. So here you have your external environment. Here you have your observations from the external environment. On this side, these are the memories. And this is the fast is on top, the slow is on the bottom. This is your saliency map of where your attention is going, and this is the expectation thing. So this is what I was talking about, the weights happening. So where you have the greater attention, you have these weights hanging faster, but you can see. So this image is extracted entirely from this and observation. So all of the black pixels and other colors come from this noisy
Yeah, or VOGL. That works really well.
Oh, that might not take it to the screen though, but I'll give it a shot. So I'm going to try VO.
That's VOSDL or GL. Try SDL first.
SDL?
SDL, yeah.
That? Never heard of that one.
Yeah, there you go.
Alright, we'll do it.
SDL is simple direct media layer.
Okay.
Yeah, it works. There we go.
So yeah, where you have this a lot of activity, it gets highly noisy, but that's because it's encoding a lot right there.
A submarine jumping around.
Yeah, this was for a Navy grant, so we had to change the movie word.
That got you your grant renewal to have a submarine in the photo?
Yeah.
Yeah.
So are these waves, the frequency of the waves related to the diffusion rate of the
Yes, they're related to the diffusion rate, but also it does depend on the original movie.
well, yeah, big.
A question just about the pressure that you use. You can look at two different colors. Yeah. So in order to do that, you scrap what could be improved. You want to just condense it all down. So you have an 8-bit value to use. You can still have 85 values for red, 85 values for green, and 85 values for blue, and just condense it. So green 0 to 55 for each of those colors, or two of those colors. Rivers, you can hence
You could have, yeah, I see what you're saying. Yeah, you could. Yeah, I mean, this was kind of the technique I was kind of going for. I mean, maybe if you have like a purple apple, you look at the red of it, then a blue of it isn't wide. That's kind of the vision I was going for. You could lose information, but you would also potentially lose information by reducing so this allows you to keep range. And but not only does it allow you to keep range, but it also, since you're alternating between the various modes, you can keep your range, but also keep multiple colors. Although this isn't that great. But if you take it down to like 2.5 modes, where sometimes the sensor can see all three, sometimes it can only see two, then your image gets even closer to yourself. So you can kind of leave one out occasionally. Although you could probably actually, instead of leave one out, you could compress them down.
Yeah, I mean, you wouldn't actually get whatever. You need a few significant. We're going to rent for how much.
So yeah, this was my undergrad research, and now I'm turning it into
Oh yeah?
yeah.
So you mentioned early on that you this cells updates in what capacity.
Well, so no, these are all being updated all at once.
Okay, so I'm updated once for each of the video.
So for you latecomers, so this is sort of a setup where so you have your external environment and this is a sensor network, and you can observe some subset of the external environment, and that these are those observations. Some of the sensors are ops, and you can observe colors of lights. And you have memories. You have a fast memory that is at each sensor and the slow memory. And you have a salience map, which allows you to control which sensors should be on there. And you have an expectation of the
Have you tried to do any sort of specific problem-solving kinds of tasks using the map that you generate? So, just trying to apply something like this to something like character recognition or to
using something on the output of it?
yeah.
No. I've just been trying to get the output up to